Optimizing intelligent operations in mathematical port modeling. Topics: Transport and logistics chains in ports and towards cleaner ports. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. Structure. The group of courses aims to train the participant in the main problems that need to be solved in the planning and advanced programming of value chains specific to industrial engineering, and more generally to engineering. It is made up of 4 courses in applied operations research. Industrial supply chains, agro-industrial supply chains, demand chains, and transport and logistics chains. Courses can be taken all in a group or individually, depending on the student's interest. Aimed at professionals, engineers, mathematicians, physicists, consultants, economists, data scientists, software developers, etc., who require and or wish to know mathematical modeling, advanced analytics algorithms, related, among others, to the implications of Industry 4.0 and its relationship with the process of evaluating the technical economic impact of the decisions that are made. This continuing education program strengthens the analytical skills and professional criteria of the participants, so that they can exercise, share and or supervise, with propriety, the professional functions in accordance with the state-of-the-art of the methodologies and technologies that support the digital transformation of the companies. Mathematical methodologies. Mathematical methodologies correspond to the scientific foundations for implementing mathematical optimization models. Specific objectives. Training in fundamental methodologies to support modern mathematical modeling. To train so that the mathematical modeling of industrial and business processes is a generator of real socioeconomic wealth frequently used in our society. Understand that optimizing the use of resources is the scientific basis of sustainable development. Learn about systems and industrial market modeling. Learn the fundamentals of modeling real problems based on the integration between mathematical models and data models. Information technologies. Computer technologies correspond to the computer tools available, freely or commercially, to design and implement solutions to problems in social or industrial organizations. Specific objectives. Learn how to implement solutions applied in the real world by making use of the modern computer technologies available for the algebraic modeling of industrial and business systems. Present and manage live tools used by large companies to solve their optimization problems. Understand the state-of-the-art of optimization and its relationship to smart computing. Know the available technologies, as the principle of basic knowledge to be able to solve, in reasonable times, problems with millions of variable. Know the fundamentals that must be had for the assembly of models using the most effective technologies. Value chain optimization or enterprise-wide optimization. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. I invite you to watch the video. Applied Operations Research and Industrial Engineering and learn more about AWO. A company's value chain is made up of 2 chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. The diagram presents the evolution of different administrative practices in companies, which are linked to technological solutions, leading to AWO. Thanks to computational power, the integration process has continued to grow. The diagram presents the original S and OP model, and the current version, which integrates more and more models. This evolution has led to modeling based on artificial hypothalamus, supported by the integration of mathematical programming and artificial intelligence. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. Mathematical models for sales and operations planning. Planting planning, inventory optimization, optimal energy management, industrial link optimization, advanced demand modeling, projection of hydroclimatic variables, harvest planning and scheduling, food supply master plans, optimizing primary links, farms, integrated planning of the agro-industrial sector, animal cutting planning and scheduling, production and distribution of concentrated nutrients, and financial risk management in agro-industrial chains. Value chain optimization or enterprise-wide optimization. Operations research uses the scientific method to address organizational problems, focusing on providing management with a mathematical basis for decision-making. It is not a science, but more the application of science, logic, mathematics, statistics, and various theories to managerial and administrative problems. It focuses on organized systems, using interdisciplinary teams of scientists and engineers. Operational research began in 1937 in Britain and developed in countries such as Australia, Canada, France, and the United States. I invite you to watch the video. Applied operations research and industrial engineering and learn more about AWO. A company's value chain is made up of two chains, strongly interrelated. Demand chain determines all the processes that are carried out to attract customers in the markets, and supply chain determines all the processes that are carried out to produce the products that customers want to consume. The diagram presents the chain of the company's production chains that together make up the value chain. One of the greatest evolutions in the modeling of companies occurs in the interpretation of their value chain. The diagram presents the evolution of different administrative practices in companies, which are linked to technological solutions, leading to AWO. Thanks to computational power, the integration process has continued to grow. The diagram presents the original S and OP model, and the current version, which integrates more and more models. This evolution has led to modeling based on artificial hypothalamus, supported by the integration of mathematical programming and artificial intelligence. The power of today's technology is not in the mathematical calculations it allows to be performed, it is in the mathematical calculations we can imagine we can perform. Mathematical models for sales and operations planning in the port sector. The following documents are used in this course. Part of the results presented have been published in the paper. Optimizing port operations to cope with shipping congestion in South American countries. Published by Informs, Institute for Management Science and Operations Research. The White Paper. Optimization of logistics operations in ports. It contains an overview of this type of project. The White Paper. Modelo de optimización asignación de barcos e instalaciones portuarias. Contains the algebraic formulation. The White Paper. Optimización de operaciones en puertos. It contains an overview of this type of project. HI has developed the HI port system to optimize the decisions of companies related to the port sector and the logistics operations that must be faced. Topic: Transport and logistics chains in ports. Port operation modeling. Framework. Ports advanced analytics. Port decision makers today face the problem of exploring ways to increase port capacity, which is influenced by the continued growth in the number of containers entering and leaving the port, the steady increase in the size of ships, as well as many other factors, previously unforeseen. Therefore, professionals, as well as academics, have become interested in port capacity management and the use of advanced analytics to support their decision-making processes. Applications can be grouped into strategic planning, business planning, operations planning, real-time scheduling of operations, productivity analysis, asset maintenance scheduling. Challenges faced. The port receives multiple weekly services that must be assigned to one terminal. The combinatorics of allocation possibilities is on the order of trillions of possible combinations. Before the project, the assignment was carried out manually, considering the characteristics of the ships, the itineraries of the services and the restrictions of the docks and cranes existing in each terminal. This assignment was made without considering optimality criteria, therefore, there was no guarantee that the established allocation would be optimal. If the terminal planer took a minute to evaluate each alternative, it was estimated that it would take millions of years to ensure an optimal response, obtained from a comprehensive enumeration. Placing a single service in the wrong terminal can easily increase the annual cost of transfers by an order of magnitude of millions of US dollars, since it would be a mistake to be commented on periodically. The table presents a summary of the problems and opportunities in mathematical models of optimization for port operations. Vessel services scheduling. Its purpose is to produce the following specific results: the transfer of vessels belonging to maritime transport services, to a dock belonging to a terminal and to a set of cranes that will serve the service, considering the operational restrictions of both the ships and each terminal, their docks and the cranes of each dock. A detailed scheduling, by events, continuous time, of the assignment of ships to the docks. This involves defining the assigned dock, the time of entry, waiting, operation and departure of each vessel. A detailed schedule of container transfers between terminals, considering the previous arrival time of the vessels. The model is operational, it is executed daily or every time an event, or a contingency, occurs that merits the reprogramming of the running program. It is based on continuous time modeling using a mixed linear programming (MIP) model. The Gantt presents a detailed schedule, by event, continuous time, of the assignment of vessels to the docks. A port is conceived as consisting of one, or multiple, terminals to serve ships of different types of transport, bulk products, container ships, vehicle carriers, and cruise ships. The main parameters that characterize the operation of a terminal are berthing lines that are characterized by the distance, draft and load they can support, the storage capacity in different types of sites, yards, warehouses, tanks, silos, the type of products that can be stored at each storage site. The image presents a satellite photo of the port of Cartagena Group, which currently has 4 terminals. The work carried out was based on the existing infrastructure in 2015, which had 2 terminals, Sociedad Portuaria Regional Cartagena, SPRC, and Conticar. The docks of the terminals are the places where ships are located to carry out loading and unloading operations. In a terminal there may be 1 or more docks, which may or may not be associated with certain types of services, for example, cruise ships, container ships, etc. The main parameters that characterize a dock are longitude, depth, and structural capacity. A terminal is made up of multiple docks. The image shows a terminal that has 2 docks. Each pier can be made up of several berths or piers, which can be of variable length. Therefore, the dock must be modeled in such a way that the length of the berthing assignment is dynamic. There is an operational restriction on the distance that must separate the ship with neighboring ships, and the start, or end, point of the berthing line. These separations can be seen in the figure. The quay will be modeled using the quay segment concept, which is defined as a range of the quay where the depth and maximum structural capacity can be considered constant. Terminals docks does not necessarily represent a physical or operational division, it is along the docking line, considered continuous, that ships are placed. The berthing line is characterized by its physical conditions, structural capacity and depth, that must be considered for the assignment of a ship to a position on the line. The physical conditions of the berthing line are not constant along its length, For this reason, the dock must be segmented to define ranges where these characteristics are considered equal, determining a dock segment, or a key. The discretization of the berthing line, for example, every 10 meters, must be defined jointly between the user and the mathematical modeler. The cranes are responsible for the loading and unloading operation between the ship and the dock floor, for products such as containers and vehicles. Normally a port has multiple types of cranes, among which stand out mobile cranes and gantry cranes. The main features of the cranes are: crane type, lifting height, seaside reach, average productivity, movements per hour, and maximum availability. Gantry cranes are located on the quays that can serve one or more berths. The limits of cranes are the reach, or the crane width, and the crane height, or the aerial draft. The height and reach of the arm is presented in the figure. It should be noted that these characteristics are common to mobile cranes. Assignment of crane to model services and handling of containers. Its purpose is to produce the following specific items: a detailed schedule of the assignment of cranes to services, and container management considering their destinations. The dock cranes are in the coastal or operational area. The transportation area supports vehicle movements, cranes, trucks and/or trains. The containers are stacked in the container yard. Assignment of gantry cranes and mobile cranes to services. The aim is to optimize the loading and unloading of vessels and maximize the use of key cranes. The model considers crane sequencing, choice of gantry cranes, restriction of clearance between consecutive cranes, sequence and non-overlap constraints, sharing a crane between two ships, and movement limitations for gantry cranes. Allocation of labor to port activities. The goal is to define the HR schedule, minimizing the number of employees hired, and reducing the cost of payroll. Scheduling is carried out considering the prior planning of port operations. Assignment of containers and vehicles to storage yards. This process is carried out in two stages. Stage 1, macro yard planning. The goal is to minimize congestion in the yard for loading and unloading. The model considers optimization based on the concept of clusters, relationship to future vessel allocation, and limitations of yard cranes. Assignment of containers and vehicles to storage yards. This process is carried out in two stages. Stage 1, macro yard planning. The goal is to minimize congestion in the yard for loading and unloading. The model considers optimization based on the concept of clusters, relationship to future vessel allocation, and limitations of yard cranes. Container and vehicle movements between ships and berths. The goal is to assign the container to the crane as close as possible. The constraints of the model are: handles the loading sequence between the shipyard and the vessel, location of containers and vehicles considering planned future movements, restrictions on cranes, clusters, and overweight and stability on ships. Real-time decisions are: what slot on the boat, and which cluster to pick up in the yard? Below, we present in detail the movements of containers between ships and berths. The dock cranes are in the coastal area. The transportation area supports vehicle movements, cranes, trucks and/or trains. The container yards are organized into clusters, composed of multiple cells. Stacks, vertically stacked container groups. Map of cells, horizontal, ground-level organization of stacked containers. Cells, in a stack, each container occupies a cell, which is located at a certain height, in a specific row. Part of the model's functions must be the stacking and unstacking of containers. To do this, the cell map is used, which has detailed information on each container, destination, or service, and merchandise. The model calculates all the movements that must be made with a container until it leaves the container yard in a service. To do this, It must be ensured that the loading time on the ship is within the ship's time window, and that the position of the container on the ship complies with the specifications given by the shipping company. The storage on the ship can be simulated as another storage area, like those available on land. This work can be carried out by the port, with a ship pallet planning system, or by the ship with its own systems. The container transfer operations at the port are: transfer between the coastal area to the container yard, using the ship's cranes and gantry cranes. Transfers in the storage area, using yard cranes, and transfer between the container yard and the vehicles transporting the containers out of the port, using yard cranes. Port operation modeling. Physical entities. A service is one of the many routes or itineraries offered by a shipping line. One or more boats may participate in a service. For the port, the following data of a service is relevant. Service name. Shipping service is one of the many routes, or itineraries, offered by a shipping line. The standard rule is that one or more boats may participate in a service. For the port, the following data of a service is relevant. Type of arrival. Irregular, randomly up every n number of hours. Regular, up to a set time every n number of weeks. Regular services take precedence over irregular ones, and deviation. If the service is regular, the deviation is a probability distribution that indicates the number of hours a service can be advanced or delayed. If the service is irregular, it is a probability distribution that indicates the number of hours between arrivals. Movements. It is a probability distribution that indicates the number of containers, or vehicles, or tons, that are embarked and disembarked per arrival, and minimum productivity required. It is the number of movements per hour that must guarantee the port to the service. The main characteristics of the service are: name of the service, type of arrival, regular or irregular, and type of boat. Ships are the entities that transport cargo. Their main characteristics are: identification of the vessel, cargo type, deadweight tonnage, length, beam, draft, air draft, number of cranes, maximum number of assignable cranes, and non-assignable cranes. Container transfers between terminals. Some containers that are unloaded are containers in transit that have to be reloaded on other ships to other destinations. Agreements exist between shipping lines for a certain number of transit containers to be dropped off by one line at the port and then picked up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which normally must be borne by the port. In addition to ships, many ports must consider barges, which are vessels dedicated to the transport of transshipment products, containers, vehicles, that must be mobilized between the port terminals. Like any other ship that covers a service, barges make use of berthing lines and cranes. Some containers that are unloaded are containers in transit that need to be reloaded onto other ships to other destinations. There are agreements between shipping companies for one line to drop off a certain number of transit containers at the port and then pick them up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which must be borne by the port. The service window defines the time between the expected date of arrival and the expected date of departure requested by the shipping line for attention in the port. The service window is divided into several times: reserve time, docking time, preparation time, operating time, closing time, departure time, early arrival date, late departure date, and time window slack. Some containers that are unloaded are containers in transit that need to be reloaded onto other ships to other destinations. There are agreements between shipping companies for one line to drop off a certain number of transit containers at the port and then pick them up by another. Therefore, if one of the lines arrives at one terminal, and the other line arrives at another terminal, a transfer will be generated, the cost of which must be borne by the port. The process of accepting a new service at the port's terminals begins with the request by the shipping companies, which provide the port with the following information: Number of expected moves. Frequency of service, weekly or biweekly. Day, expected time of service arrival, or time window. Physical characteristics of the type of vessel that will provide the service. Based on the information provided by the shipping company, and the current assignment of services to terminals and docks to ships, firm commitments, the commercial area, supported by the operations area, analyzes whether it is viable to provide this service in the port facilities. To do this, it must be to that. Accept a new service. It is important that the port can negotiate minor changes in the service window with the services already in place. Although within the negotiations there is a permitted slack, +/X hours, in the service window, this should not be included in the process of assigning services to terminals and from ships to docks. There are some services that have pre-scheduled appointments, for example the passage through the Panama Canal, so the slack in the departure time must be 0. The hourly fine for non-compliance with the time out of the time window has an average cost in US dollars. The fine depends on many factors and it is not possible to settle it in the same way for all shipping companies. In many cases it is contractually fixed. Sliding optimization. There are two alternatives for port modeling. Integrated, applied to small ports or terminals, and decoupled that is required for large ports or terminals. In the case of the Latam port, the methodology called slide optimization was used. The idea of sliding optimization is that, although an integrated system implies that all its variables are related, and that therefore their optimization must be joint, to the extent that two variables are distant in spacetime this relationship tends to fade, and it can be thought that at the two extremes the influence disappears. Sliding optimization divides spacetime into sub-problems that are solved sequentially, starting with the first and covering the space bounded by the B ships. The time is determined by the departure cutoff time of the last ship of the problem. Then the next problem is added, which overlaps the last ships of the first problem, and introduces additional B ships. This is to ensure a smooth chain of sequential issues. When the problems that cover all the ships have been solved, all the problems together completely cover spacetime. Sliding optimization allows to move from an integrated approach to a decoupled and coordinated approach. Sliding optimization. The first stage of the methodology is the solution of the allocation stage. Considering that the decisions to assign services to terminals are the ones that set the tone for the operational cost, related to any ship service scheme, it is feasible to solve the assignment problem in a first stage. This problem is solved in a short time, and the quality of the solution can be very close to the best possible. This has been proven empirically for ports, but not mathematically. Knowing the set of S/K services that must be operated in each terminal K, the optimization is carried out to schedule the services based on a solution dynamically partitioned along the timeline of each terminal. This activity forms stage 2. The steps to follow are described below. To carry out the programming of a terminal, the first N services are taken according to the expected date time of arrival at the port. With this subset of services, high port gets a schedule that minimizes the departure time of the last ship within the N scheduled ships, which guarantees that for the following SKN services the greatest amount of time is available for its programming, which facilitates the feasibility of the problem. The value of N is determined empirically based on knowledge of the behavior of the system. The first consists of a set of additional constraints that measure the deviation of the windows of the services that close the planning cycle, and the second is the objective function that is to minimize the cost of the operation, which includes minimizing the payment of penalties for noncompliance in the service window, and a penalty of deviations from the service attention windows of the services that close the planning cycle. As a result of Stage 2, a feasible initial solution to the programming problem has been created, close to the optimal solution of the problem, and this allows the algorithm to move to Stage 3. In Stage 3, high port proceeds to run the optimization integrated for all the services that have been assigned to each terminal. The feasible solution built in Stage 2 is provided as an initial solution to the problem that is solved in Stage 3, which is not identical to the model used for the creation of the initial solution. Sliding optimization divides spacetime into sub-problems that are solved sequentially, starting with the first and covering the space bounded by the B ships. The time is determined by the departure cutoff time of the last ship of the problem. Then the next problem is added, which overlaps the last ships of the first problem, and introduces additional B ships. This is to ensure a smooth chain of sequential issues. When the problems that cover all the ships have been solved, all the problems together completely cover space-time. Slide optimization allows to move from an integrated approach to a decoupled and coordinated approach. In the case of ports, high port works based on 3 stages as presented in the following diagram. Below are some results of the application of high port to a LATAM port, following the methodology described above. Outputs. Below are some shell windows containing the results tables of the models of high port. The screenshot displays an Optex Explorer of windows for the output of a model. The selected table points to the variable time of entry of the ship to the dock. The image presents a selection of a pivot table in Excel with the schedule of services per key. The image presents a pivot table with the crane utilization time per service. This is a Gantt chart of keys, cranes, and ships. This is a Gantt chart of keys and cranes. Topic: Towards cleaner ports. When we talk about cleaner ports, we are talking about them in all aspects. This implies pollution of all kinds. Design of port and railway megasystems. The growth of the port sector, driven by the growth of maritime transport, entails the execution of megaprojects aimed at the construction of sustainable port and railway systems. This is an opportunity to use operations research methodologies for regional planning, including semi-detailed port operations. These models must be integrated to quantify the impacts of port region decisions, to carry out regional planning that maximizes the well-being generated in the social surplus, and that guarantees the sustainability of development plans. In the case of regional planning, an example of the physical systems associated with autonomous, real-time optimization models that communicate with each other are inhabitants, installations or equipment, energy, land use, companies and industries, and transport and logistics. Below, sustainable ports will be analyzed from the point of view of emissions. First, energy efficiency, integrated analysis of minimizing the cost of energy supply and minimizing environmental impact. It is a bi-criterion problem, since the two minimizations move in opposite directions. It implies redesign of the energy supply chain to the port and its ecosystem, including all available power technologies. Simulation of the optimal integrated operation of port operations and energy supply. Implementation of a smart grid to handle integrated port operations and energy supply planning and scheduling. Second, port region integration, integrated analysis, through a regional planning model, of the relations between the port and the region, to develop actions on the territory that improve the quality of life in the port region ecosystem. It implies implementation of a regional planning model that includes the impact of the port in the region. Analysis of the main port region problems. Integration of multimodal transport services for containers and bulk materials. Third, environmental control of the waterport ecosystem, integrated analysis of the pollution processes of water bodies and determination of the actions that must be taken to maintain the ecosystem environmentally sustainable. It implies implementation of a finite elements pollutant dispersion model in the aquatic system. Implementation of an optimization model that integrates an optimization algorithm with the simulation of contaminant dispersion. Remote information capture to project the boundary conditions of the body of water, in space and time. Weather planning of the trip on the boat. 3 aspects must be taken into account in fuel consumption, and therefore in the emissions generated. Tidal height, wave height, marine currents, and motor speed, depends on the type of motor. Additionally, the characteristics of the boat must be considered, including the dead weight and the additional load. To quantify the importance of what we call trip weather planning, the best solutions from the selected test instances for both mixed weather and bad weather scenarios are compared with the performance of the programs performed assuming good weather throughout the planning period. It should be borne in mind that, from the point of view of fuel consumption, the efficiency of an engine is not given at the maximum of its power. The minimum unit cost per RPM is close to its maximum capacity, in the graph 80%. From that point on, as the ship's speed decreases, the amount of fuel consumed per unit of displacement increases. If RPMs increase above optimal capacity, the unit cost increases exponentially. On the other hand, these curves change depending on the weight of the boat and specific sea conditions. This behavior is independent of the size of the ship. The graph presents the fuel consumption curves as a function of the ship's speed. There are 5 curves, for different revolutions per minute, which are related to different blade pitches. The exponential nonlinearity is evident. Energy savings in train control optimization. The need for a clean environment is based on a rational consumption of energy. This covers all industries, and in general all human activities. Optimal train travel speed planning involves mathematical modeling to minimize energy consumption when the train has a predefined maximum arrival time. First, it must be considered that all industrial processes are variable speed, and that energy consumption, depending on the speed of the process, is nonlinear, it is exponential. This implies that, in the absence of economies of scale, the regulation of the speed of industrial processes is fundamental in the process of controlling energy consumption. Production facilities do not have a defined capacity, it is set according to the speed of the process, and the time that this speed lasts. That is a decision variable of industrial operations. The table presents the energy consumption versus speed of the AB103 high-speed train. The column 2 shows the kWh consumed per kilometer for 3 speeds analyzed. The nonlinearity is noticeable. As a vehicle increases its speed, when it is operating above its maximum efficiency, the unit amount of fuel consumed increases, which implies higher variable costs. However, increased speed means increased production capacity, which lowers investment costs due to increased vehicle use. The optimal decision is not obvious. Truck speed modeling is very important in long-range travel. In state-of-the-art cargo transport vehicles, the engines are electronic, digitally controlled, with telemetry capacity from the nearby environment. This autonomous capability may be called optimal short-range control. However, there is another level of vehicle operations planning that is long-range, and related with the total journey. The problem of optimizing energy consumption, gasoline, diesel, natural gas, propane, or electricity, is complicated because the energy function is nonlinear, and depends on factors that are the result of the decision-making process, such as the load and the position of the truck in any moment. Additionally, exists exogenous factors that define fuel consumption, depending on the vehicle and the route. These may be divided into static, for example, slope, rugosity, etc., and dynamic, that depend on traffic and route weather status. High can incorporate the modeling of the speed of the vehicle as one of the decision variables of the routing model. The fundamental idea is that the arrival time is the result of coordinating time windows and fuel consumption, so as to minimize the cost of fuel throughout the total journey. In this way, the truck will arrive just in time, not a minute before or one after. Emissions estimation in multimodal transportation. Ports play a key role in fostering the growth of trade and national and international economies. As ports continue to expand in size and capacity, the impact of their operations on air quality and climate change becomes increasingly significant. While nearby regions may experience economic benefits, there are significant concerns regarding the emission of air pollutants, which have adverse effects on both human health and climate change. Predictive modeling of port emissions is a valuable tool for identifying areas of concern, assessing the effectiveness of emission reduction strategies, and promoting the sustainable development of ports. The main objective is to estimate SO2 emissions from ships during various port activities, including hospitality, maneuvers and cruises. The objective is to obtain information about emission patterns and explore strategies to mitigate their impact. Transshipment operations in intermodal terminals. The article, Modeling Carbon Emission Estimation for Hinterland-Based Container Intermodal Network. It contains the case presented below. To address growing environmental challenges, the analysis of high-carbon transport systems seeks to achieve carbon peak and carbon neutrality goals, calculating the carbon emissions estimate and identifying carbon reduction drivers for the inland-based intermodal container network. The impact of transport vehicles on climate change is often analyzed from the well-to-wheel (WTW) perspective, consisting of two phases, well-to-tank (WTT) and tank-to-wheel (TTW). WTW is a life cycle evaluation mode developed for transport fuels and energy carriers that cover resource extraction to vehicle operation, excluding the vehicle's life cycle. In the TTW mode, electrical energy is estimated to be zero carbon emission. In the existing studies on intermodal emissions, there are few works that distinguish between the two emission modes. Well-to-wheel, WTW, and tank-to-wheel, TTW. Taking the port of Shanghai and the Yangtze River Delta as a case, carbon emissions from the last 10 years are used for well-to-wheel, WTW, and tank-to-wheel, TTW, modes. The critical factors that drive sensitivity analysis and the variation of carbon emissions in different scenarios with carbon reduction policies are identified. The results indicate that the transport structure and fuel choice significantly affect the reduction of grid emissions. In the current policy-based scenario, WTW mode peaks carbon between 2030 and 2035, while TTW mode peaks earlier. The image shows the aggregate structure of the case data and the results. The image shows the sensitivity analysis of the key parameters. Topic: Smart ports. New opportunities in artificial intelligence. First, global capacity shortage. Capacity shortages are evident in many of the container terminals at major seaports. Some of the main reasons for this are the continuous increase in the number of containers around the world and the increase in the size of ships in both production and use. Other reasons are the export of products manufactured by China between multiple regions, the trend towards moving production facilities to low-cost countries, and the impact of rising GDP levels on the volume of world trade. All these factors, individually and in combination, contribute to the problem of capacity shortages, and this has many consequences. For example, capacity shortages accelerate congestion at seaports and increase costs and delays for shipping lines, terminal operators, transport companies and carriers. Secondly, due to the problem of capacity shortages, large container ships can only visit a limited number of ports. Third, the issue of capacity shortages increases the transport costs of specific port routes, and therefore other less congested ports become more attractive to users. Second, customer value. In a customer-driven market, the focus is primarily on the perceived customer value of the entire relationship with a company rather than on the product or service. Supply chain management is naturally an important component of meeting customer needs and providing value. The importance of customer value is one of the main research agendas, and the role of the client in maintaining a long-term relationship between the chain of partners has been investigated, in some industries, such as the pharmaceutical supply chain. Customer value is an important factor in determining the type of supply chain needed to serve customers and the type of services to retain them. A company seeking competitive advantage must clearly understand its customers' perceptions of value and the product attributes they demand. Perceptions of value differ between customer segments. Therefore, a company must identify the customer segments that are important to its long-term success and adjust its ability accordingly to deliver value to these segments. Third, port pricing. The level and transparency of prices are decisive in the choice of supply chain and mode of transport by shippers. Port pricing structures are related to the cost of I. Port of call charges, 2. Freight handling fees, and 3. Congestion charges. The current practice of port pricing is based on a fairly linear structure and does not incorporate modern pricing tools, such as price differentiation or revenue management. The complexity of current port pricing schemes is striking. When calling a port, ship operators are commonly presented with a detailed menu of services. Prices reflect the diversity that exists in terms of the type of services and the rules of services offered, as well as the port entities or operators that offer them, and whether the provider is a private company or a public infrastructure provider. The result is a non-transparent pricing structure that complicates port choice for ship operators and cargo owners and thus softens port competition, and competition between container lines. These multi-pricing structures reflect the fact that ports are complex service centers offering a considerable range of services. Associated costs are generally organized into three categories. Port calling costs: we refer to the costs of all services offered to the ship, ranging from access to the dock or terminal, to piloting, to water supply and bunkering, fuel supplies, that is, they cover all the costs of handling ships. Terminal handling costs, comprising the costs of loading or unloading, storage, customs clearance, repackaging and forwarding, i.e., covering all services necessary to move cargo forward through the port and into the supply chain. Concession prices refer to the cost of acquiring a dedicated terminal. The focus on port operations, operation and competitiveness has increased in recent times as a result of tougher competition between alternative supply chains in trade and transport, high alternative costs of coastal areas, high infrastructure costs of ports and, finally, the long-term but so far rather unsuccessful policy of moving cargo transport off congested roads towards the sea and the railway. The course group director is the founder and executive director of RCADT. Engineer Velasquez Bermudez's experience in applied operations research dates back to 1972, which means that he has accumulated 50 years solving real-world problems doing engineering consulting using mathematical models. The table presents the plan of topics foreseen for the course Holistic Optimization in the Port Sector. R-CADT is the most applied academic center in the integration of the teaching of mathematical programming and artificial intelligence. For more information you can consult the URL. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.